We're being heard, and it is 9 a.m. out here in beautiful Federal Way, Washington, town that has an identity crisis because it's named after a street. So, but I'm right outside of Seattle, Washington, and we are back for the second live webinar of the MTConnect Student Challenge. I want to welcome you for joining us today. A couple of quick housekeeping things before I introduce our illustrious guests down below me here. Like I say, my name is Steve Miller, better known as Kelly's dad, marketing gunslinger, and I am the facilitator for this. And all that means is I am the facilitator for this, okay? So any questions, these are the smart ones below me, okay? This is like I've got the triad of MTConnect intelligence underneath me here. We are recording this, so this will be available for review afterwards, just like we did record last week's program, and that is, it is either available or it's going to be available. Helena, before I introduce you, can you tell me where that is going to be?
It'll be on YouTube.
It'll be on YouTube?
Yeah.
Okay.
Yes.
All right.
We will send out a follow-up email that has links to both this webinar as well as last week.
Okay. All right. And so thank you very much. You know what I forgot to do also is I forgot to, I need to, at some point here, and I'll do it once we get started, I need to mute the audience. But anyway, so we're back, and we appreciate this. We're archiving this. As you can see down below, all the way at the bottom, we also have a place for you to enter any questions that you have during the session. What we might do, since this is part 2, and we ran, I think it was about 50 minutes, 40 or 50 minutes of this video of Will giving a presentation at some university on the West Coast somewhere, not sure where, but so we're going to run the second part of the video all the way through, and but if there are questions, we can certainly, and I'll leave it up to Will and Tim and Helena, we can certainly pause the video and answer your questions as we go, or if it's something we can wait and answer at the end, then we'll do that. So let me introduce who we've got here, because like I say, I am just, I'm kind of the low guy here trying to figure out what's going on. I can tell you all about Einstein's Cross, but I have no idea what I'm talking about here about MTConnect. But Helena, Hailu, did I say that again right? Hailu?
Yes, you did.
Thank you so much. I always want to make sure I pronounce people's names right. Helena, who is actually the mastermind of this thing, of this whole putting this thing together here, is the MTConnect product manager at the MTConnect Institute that is part of the Association for Manufacturing Technology. And we thank you for joining us here today. Right below her, trying to hide from the screen, Tim Shinbura, who is the VP of Manufacturing Technology. Obviously he is the man, since it's manufacturing technology also for AMT, and Will Sobel, who is the Chief Strategy Officer for Systems Insights, and he is affectionately known as the godfather of MTConnect. So I welcome you guys. Helena, can you give us a quick little background of MTConnect and the Student Challenge, I should say, for us, and before we get into the video?
Sure. The MTConnect Student Challenge is an innovation competition that is targeted specifically for college and university students within the United States. The competition is sponsored by the Office of Secretary of Defense, Defense-wide Manufacturing Science and Technology Program, and it's executed by organizations such as
all guests have been muted,
such as AMT, MTConnect Institute, U.S. Army Benet Lab, and CDMM in partnership with NTMA and SME. So the competition is a two-part competition, two completely distinct parts. The first competition is an ideation competition where students could write a 5-page proposal where they identify a need within the manufacturing industry and propose how they would solve, how they would meet that need or solve the problem that they've identified. The second competition is an application competition where students would develop a software that addresses a need within the industry again. And what we're asking for submission there is just a video of the working application as well as an icon and an abstract that describes the challenge within the industry as well as what the solution or the application does to meet it.
Mm-hmm. And if they have any...
the deadlines, important dates are coming up. December 15th is the deadline for the ideation competition, and January 31st, 2016 is the deadline for the application competition. Okay.
Okay, great. And for more information, they're going to be able to go out, and we'll put some more, another visual up, another slide up later on, but for more information, they can go to where?
For more information, they can go to challenge.gov/challenge/MTConnect Student Challenge Ideas, or they can go to challenge.gov/challenge/MTConnect Student Challenge App. That's very long, so we will put that up.
Yeah, we will definitely put that up, but I'm going to put this up right now, so if somebody wants to contact you directly, they can they can do that, and we'll show those other links a little bit later on. And before I get into Will, let Will introduce what we're going to be watching here. Tim, do you have any hellos or comments you'd like to say right up front?
Oh, this is just an exciting time, man. I hope people take this in, they consume it, do some good stuff with it. We've had a lot of great productivity, you could say, when we do these types of challenges. So can't wait for this year's stuff to come out.
Yeah, I agree. It's this stuff is I think this stuff is fascinating. Even though I'm not an engineer, I used to play one on TV. No, I'm kidding. I was the son of an engineer, so I kind of know how you guys all talk in acronyms and everything like that. I get that. And this whole thing sounds very exciting. Okay, so Will, now I'm going to start a video here that's picking up where we left off last week in your presentation. What can we see? What kind of give me a synopsis of what we saw in last week's video, and what are we going to see in this week's video? Whoops, Will, we're not hearing you. Did you mute yourself? One of the things I love about technology is we got stuff like this going on. So, are you logging back in? Are you calling back in? Well, okay, we're not hearing Will. So maybe Tim or Helena, can you introduce this? Helena?
I'll take it. Last week, the webinar was focused mostly for those who want to participate in the ideation competition. We went over what opportunities exist within the manufacturing space, as well as barriers that exist. One of the things that we talked about.
Okay, go ahead and finish, Helena, and then we'll let Will say something.
Sure. One of the things we talked about there is data. Data is either not being collected or not being used within the manufacturing industry. So this week we're going to talk about how MTConnect is an enabler of data-driven manufacturing, because it enables companies to collect data from various types of equipment and then later analyze that data and turn it into actionable information.
Okay. And Will, you got anything to add to that? Was that a Jger that you just shot? Well, anyway.
No, that was my coffee.
Okay.
It's actually what fixed my phone, my audio.
Yeah, no problem. We're glad you're back in.
Yeah, so actually I couldn't hear what Helena said, so I'm sure it's all correct. And let's see. Yeah,
And
so
we're
we
going to,
got through, we went through from the drivers to what small to medium manufacturers were, then went into a little bit about blockers, and then talked, this section that we made about halfway through was just on the MTConnect standard and what it enables. The next sections that we're going to be talking about are machine-to-machine integration and protocol and other areas of the information model, basically how the standard is put together and how the information represents itself.
and we're going to watch this video. I don't know exactly how long we're going to be watching this, but we're going to stop at some point, and instead of watching the balance of the video, then Will is going to take over and do the final presentation, the end of the presentation live. So like I said, once again, if you have any questions during the presentation, please feel free to enter them in the Q&A section down below. And with that, I'm going to go ahead and start the video, and we'll be back again in just a few minutes.
As we start to bring data from various different systems together, and as we start to integrate it, the idea is that we're going to bring multiple different services. So if we look at, let's say, equipment manufacturers, this is the area that we're providing. MTConnect is really a service. You think about it as an HTTP RESTful service where you make a request, you get data back, and you know what the data means. That's what this guy is here. Eventually, design systems and supervisory systems and engineering systems at different levels will also be providing services that we can then integrate these things together. And this is the first step of being able to get interoperability between multiple different systems. That's how we're going to be able to make, if you talk about, next industrial revolution, by interoperability and integration of data and services from the entire digital thread, that's how you get to that point. And that's how we can start to achieve some of these things like self-optimized and self-aware systems. So from the point of view of what we can do now, we're really talking about these continuous improvement processes. So we talked before about the idea that you're continually trying to improve your business and trying to make more money and so forth. And to be able to do that, you need data. So we really need to look at things like optimizing your execution processes and keep optimizing those. I mean, once you get to a certain level of productivity, you can always get more productivity out of it. You can always find better ways of doing things, improving your processes, and increasing your workforce training. MTConnect can actually be used in some ways for workforce training. If somebody is executing a process and they know how that process works, you can actually capture that process and then check to see if the process is still being executed in the same way as it was before. This is a big issue. We talked a little bit about distributed manufacturing. I want to be able to move a process from one location to another location. Well, we actually call it tribal knowledge capture, where I can then say, I'm going to capture how it's done over here, the exact steps and the exact feed speeds, tooling, all the information about how that process was executed, and then be able to replay it. There's actually an issue in a lot of SMEs that have been doing processes for many, many years. In that video, we heard that a lot of times you get your three-dimensional model, you then snap it down to a 2D drawing, and then you build your processes off of that. The problem is that then you're into sort of the paper realm. And a lot of what it takes to be able to get that part, after you go through the iterations and the prove out and so forth, to a stable state where you can make that a good part every time, a lot of that information about what it takes to actually do that is lost. Or it's in the head of the guy who's executing it. The operators are the guys who know how to do it, know how to make that perfect part. And that's great as long as they stay, as long as they don't retire, nothing happens to them, they don't get sick. But if that person or that set of individuals, if she doesn't come in or she gets sick or something, you're going to get into a knowledge gap, and you're going to have to rediscover how that process was done. So part of what you can do with collecting data is you can collect how processes are executed. This has benefits in being able to make sure that you can repeat a process, that you can train new people on how to execute that process, and also tell why first shift is 3 times more productive than third shift. what are they doing differently? Often it's not just because third shift is screwing around. Often it's because first shift has either been trained or there's some special trick that they know that the third shift doesn't know, and you need to capture that. So data can help you capture all that. Tooling optimization, we actually do tooling optimization where we crowdsource tooling data from sites and then find optimal tooling strategies. So you can do things like that. You can actually figure out, what is the best way a tool can be used for a manufacturing process. You can predict quality, you can predict yield, things along that line, by being able to find what is highly correlated with a good part. If I'm checking tolerances, I'm checking my production processes at each step, I know where things are going wrong. Strategies of how to manufacture something, processes, etc. And then design for manufacturing. Looping back to engineering, basically I can say, okay, this is how execution, when I engineer something and I create a part program and a tool path that does this is how it is actually executed. This is the efficiency. Talk a little bit about that. There's a couple of research projects we can go over. The other place is going all the way back for design. In other words, if I design a feature in this way, this is the entire chain. This is how it's going to come out at the end. All the way through the engineering process, the tool paths and so forth, and then to the execution. So often in the engineering stage, there are a lot of assumptions made about how it's going to be executed and simulation and so forth, but often that doesn't actually come out right because the machines don't quite operate the way simulators operate, and things don't quite work the way they do in an idealized world. Physics and reality come into play. So we need to understand exactly how that translates, and by collecting data and analyzing data, we can actually get to the point that we can start to make predictive assessments of these things. And the other area, when we talk about process, is basically what we talk about more self-aware. I've come back to this a few times, of being able to redirect. So if I have a failure, we can work around failures. We can even go, if we want to, we can assess the trade-off between doing something externally or doing something internally. So if, let's say, I want to manufacture at another site, and that's actually going to be more efficient than if I try to do it locally, I can do that. I can make these assessments because I know the actuals. I know how things are actually going to play out in my manufacturing process. And that's where we start getting into what we were just talking about. Industry 4.0, digital manufacturing, and predictive, and so forth. All these big words that everybody's talking, or big terms that everybody's talking about these days. That's how you're going to be able to achieve it. Another area that we've worked on within the standard is machine to machine and automation. And we have an interesting way of doing it. Is anybody here working on like robotics and process automation, things along that? Okay, kind of, good. At least, okay, see what you think about this. So one of the issues that we ran into, actually I'll jump forward a couple of slides and back it up later, but was the fact that most integration of systems started with sort of a 24-volt wire connecting two different machines together and working with PLCs. So this is actually from last year. This is a robot-ready option for a Haas controller. I mean, most controllers do it. Akuma and everybody else does it this way too. And basically, it's just a bunch of wires, and you have your different clamps, unclamps, cycle start, door open signals coming back and forth. So it's just pretty much about, what is that, 5 or 6 binary signals going back and forth between your machine and your robot or your cell controller. The problem is that this solution here, if we think about it, you have a cell controller, you have a bunch of PLCs which integrate these different systems together, custom interfaces all over the place, and you're dealing again with these sets of wires and this multi-level sort of binary signals going back and forth, and then some vendor applications there to be able to support the integration of these systems, and often they're just one-offs. They're pretty bespoke. If you look at most cell setups, they're pretty one-off type solutions. We were trying to get into a cheaper, simpler alternative. I did a project with NIST and Ross and NCDMM where we integrated machines and robots together using sort of a simple IT-based approach where we just connected through the network the device control, the machine tool and the robot, and created sort of an executive process which received real-time data, but highly semantic data about what these machines were doing. And basically the way it worked is each side was listening to the other side. So if we look, the machine tool listens to the robot, and the robot listens to the machine tool. And we spoke at a high, what I call semantic level. So instead of binary signals, we were talking about what the part was. And we're talking about the things like the robot didn't say, move, or the machine didn't say, robot, you move to this position and get this, pick up this piece of material. What it said, the machine tool just said, I need a piece of material. I need something to do. I'm ready to accept material. So there's a interface that we created called material load, and if the machine tool says it's active, it's waiting for something to be able to fulfill that need. A robot, or it could be anything, really. And then the robot then says, okay, I've taken your task and I'm executing your task. And then the robot asks the machine tool to do things like open its door. And the machine tool then says, okay, my door is now open. And it says, okay, I need you to close your chuck, because it knows the machine tool needs to hold the material. And then it waits for that to be done, then it knows it can release and retract. And then it tells the machine tool, okay, now it's okay for you to close your door. These are just requests that are coming back and forth. It's not actually telling it, it's just saying, I'm requesting that you do this, and so we can get a complete operation. The idea is when we elevated everything up to that higher level semantic, we found that was actually pushing the intelligence out to the edge devices. So instead of having a centralized control system which is trying to orchestrate all the behavior of all these different systems, we had each system kind of taking care of itself and knowing what it needs to do. And by distributing this intelligence to each of the edge devices, we found that we had better resilience and no single point of failure. And we also had a dynamic system where we could change over parts. Instead of communicating just a single byte, now the robot was saying, I picked up this type of part. I know the part ID. And the machine tool can say, okay, and especially with the new stuff that we're coming out with in our parts addition to MTConnect, the machine tool can say, okay, I know what part program I need to run for that part. I know what the processes were before me and after me. I know all this information about this part. So it has this rich information model now about the process it's about to execute. And the machine tools are able to make intelligent decisions, and the robots are able to make intelligent decisions, and basically you get this next step of dynamic flow. So that's another area that MTConnect has dealt with, this idea of dynamically connecting devices together and having them communicate, but at a higher semantic level. I found that we weren't actually the first ones to do this. It was done, I think, at MIT back in the 80s. But the computational power necessary to be able to run, just coordinate the messaging, was not there, and the networking wasn't there. And the cost saving was huge. So if you look at the advantages to the SME or the manufacturer, we got rid of all the PLCs. We got rid of all that, the additional equipment. We were able to get to just a couple of applications running on either side. Yeah, so the question was, does the machine need specialized sensors and other equipment to be able to interoperate? And the idea of this was, yeah, right now there are special requirements because the machines don't come with it at this time. We're starting. I mean, the idea of the standards and the reason you create open free standards is so that you can get machine tool builders to then implement. So, let's say if you bought a new Mazak or a Kuma or Mori type machine, or any machine like Haas or whatever, and it came with this interface ability built into it, we were trying to get to plug and play. So I'd be able to plug in my robot to that machine, and it would just be able to communicate. Well, we have a project going on to actually prove out some of this, where machines will be discoverable. Location will be discoverable as well, where the machines will be able to communicate their capabilities, and you'll be able to understand where they are and what they're capable of doing. And then you won't need special technology. Basically, even with things like, let's say, take a universal robot, which you can then put without an enclosure, and if you could just park that in front of a machine. I know a couple of shops that are doing this, but it's very simplistic process right now, because things like the robot actually has to push the cycle start button. to get the cycle going, because a machine doesn't have an easy way to be able to integrate that information. So the next step forward in automation is really to be able to, first off, raise it up to a level where you're not dealing with individual sensor signals, where you're dealing with higher level semantics and able to communicate the entire manufacturing process. And then the next level, to be able to get the devices to the point where they can discover each other, and then you can get into plug and play. So that's where we're going with this. Actually, I might just skip over this. It was a little thing that I did. But that's just a little video that I made a long time ago about integrating it together.
The system's architecture used the MTConnect ROS industrial demonstration at NIST made use of the MTConnect read-only communication strategy, where devices do not directly control each other. They publish their state using an HTTP server, and the other devices perform actions if they are capable to do so. In the demonstration, we use a robot and a machine tool. The machine tool does not send messages to the robot. The machine tool requests data from the robot, and the robot from the machine tool. For example, when the robot changes its open door state to active, the machine tool responds by transitioning its open door state to active. Once the door is open, the machine transitions to complete, and the robot acknowledges by transitioning back to ready. The roles are reversed when the machine tool makes its load material request from the robot. This is peer-to-peer communication. The benefits of this architecture are the ability to scale from a single device to multiple devices, even different types of devices. When the new devices are added, the communication between devices is identical to the one-to-one scenario. This architecture easily extends support of many-to-many communications, which enables fault-tolerant processes that are driven by demand and availability, not a preset sequence of operations.
Yeah, so that's kind of a high level of what it is. So basically, we proved this out actually at NIST and had.
So Will, is this where you wanted me to pause? I will.
I'm now unmuted.
There you are. Okay, so this is
Here
where
I
you want
am.
me to pause, right?
Yeah, I was wondering if anybody who's watching has any questions or would like any
Oh,
more
yeah.
information.
Yeah, that's good. Are there any? Oh, whoops, I'm messing with the list here. So I don't see any yet. So so should we continue with this, or did you want to switch over to the other part yet?
No, let's keep going.
Okay.
This section is on some of the research projects that have been done. These are some examples from a couple of other people who work with MTConnect.
Okay, great.
Okay,
Here we go.
let's go.
Incredibly good results as far as resilience and the ability to have the processes self-recover. So when something went wrong, pretty much just picked up where it left off. And the machines, because the robot wasn't dependent on just a very narrow view of the signals, it could tell what's happening on the machine tool. They were reporting their entire state. We were able to make intelligent decisions about how to recover the process and how to carry on. And that sort of edge-level intelligence, we're able to push more of the intelligence to make these devices more intelligent, get away from the single-wire solutions, will, I think, bring in a new set of, a new era of automation. That's my hope, anyway. So I'm going to go through a couple of research projects. These were actually done at various universities around the world, and this one's over at UC Berkeley. Give some ideas of some things that people are working on right now, and I'll talk through some others that are going on. So this is actually by Ronak, and he did some predictions using machine learning on manufacturing processes, basically efficiency and so forth. And he's working at the LMAS. He's doing his PhD at LMAS, which is the sustainability group over at UC Berkeley. So a lot of it's around energy and energy efficiency of different machining strategies. And pretty much what we talked about, he did. So he took process parameters, took them into the machine tool, added additional sensors in. Again, we talked about sensor fusion. pumped that into the MTConnect agent, and then processed all that, and then developed processes to extract knowledge from the manufacturing data and then feedbacks. This is just like an optimization feedback loop that he created, going from the data coming off the machine, the sensors, gluing it together, and then improving the process. And the hardware was pretty simple. Basically, just take Data Moriseki. This is a little mill, micro mill, with a FANUC controller, and he added a high-speed power meter. This gets you 100 hertz power sample data. If you're interested in getting any of this type of kit, I can also try to hook you up with some pieces of equipment that, some sensors and other things. We have a few different options that, we can give away. Then he popped it into a switch, and then that was aggregated in an MTConnect agent. MTConnect agents can aggregate data from multiple devices, so you can have, we've even had like 50 different machines hooked up to the same agent. The agent, again, is that protocol server, so that's your point of contact for getting information from machines. And so we had the data from these different areas collected up, and this is your controller data. So speeds, feeds, loads, the actual code that was being executed, so we know the block and line of code that's being executed. And we know how much power was coming off of the 3 phases coming into the machine. And he did this condensation and then simulation. So it was a 2-phase approach. So he's basically trying to collect data and then simulate based on what he collected. And then you're able to take that data in for higher levels of data. So if you talk about the pipeline, after you go from semantics, you then go to what we call enrichment, where you take the data that's coming out of the semantic model and you start to derive additional meaning to that data at a higher level. So things like depth of cut, toolpath strategy, cutting strategies, volume of material removed, and so forth. This doesn't come from your machine doesn't know how much material it's removing, it doesn't know how fast it's removing it, it just knows what it's doing. It's doing the motion and everything else and the positions that it's at. And by using and combining it with your process data, you're then able to come up with higher level abstractions, and that's what that is. So that's what we call sort of an enrichment, where you take it and get to the higher level of knowledge and assessment. So then, again, went through this whole pipeline. Then you could do simulation, so you could make changes and then simulate what those would do and compile it and then create these models. And these are higher dimensional models. So basically, he was going through this whole process of modeling based on what he was observing. And this is getting a bit too deep for me, and you can actually ask him. He's a great guy. He wrote UC Berkeley about how this actually worked. He wrote a paper on it. But he was looking at these different dimensions, basically your spindle speed, feed rates, direction of cut, cutting strategy, length of cut, and so forth. These are all the different attributes he was taking into consideration. And then he was looking at the energy used for each of these different strategies and trying to optimize around that to predict the characteristics. And this is the sample part that he used. And some of the different, he has test parts and various different strategies. And again, so taking a look at these different strategies of cutting and toolpaths, his objective was to be able to predict how well these different strategies would work by being able to observe how they worked in the actual energy profiles. Because when you're going at it from a purely sort of first principles model, often things don't match up when you actually go to a machine tool. And by actually testing this thing on the machine tool, he was able to tell, it's not just around speeds and feeds, it's about, there's a whole bunch of other motion and various other loads and so forth that take place, and some of the physics, and basically he was able to optimize a model around that to find an optimal energy efficient toolpath for pocketing. So anyway, that's one of the projects that was done with MTConnect. And again, using MTConnect and being able to fuse the high-speed sensor data with the machine tool states, the blocks, and every execution states of the machine, he was able to then pair everything up and know exactly what operations were taking how much energy to be able to do this analysis. So this is actually done at IIT Madras, and we have an office over in Chennai. So this is one of the projects that we do over there. And this is actually an interesting, the idea here was to reverse engineer a machine tool from some base principles, but use real data collected to be able to do it. So they built a machine which was just basically a load and a generator. I'll have a picture of it in a second. And then collected 100 hertz data again from a high-speed power meter, and then put it into a simulator and was able to simulate pretty accurately the machine tool behavior. So this is the rig they came up with. It was basically a 3-phase AC motor with a coupler and a DC generator, which would put a load on it, and then a relay bank, which was pretty much just a whole bunch of these huge relays that they stuck together. Did a nice job of heating up the room as well. And then a load bank that was controlled by an Arduino, which would then switch various resistors on and off to simulate different load patterns to be able to simulate a real manufacturing process. And then also adjusted the power going into the motor to be able to simulate speeds and the speed of the either the axes or the spindle. I mean, of course, manufacturing, metal cutting, you have to really focus on spindle speeds. And that little microcontroller here was just an Arduino. So a pretty simple, cheap kit. And then the simulated data would be the data that was pumped into the system so that we could simulate the behavior of the machine. So one of the first things they found out was how fast you needed to sample. So it was like, how fast is good enough? And they tried at 1 hertz, 10 hertz, and then 100 hertz, and found that with 100 hertz, they were able to get a fairly good fit of the spikes. The problem is that if you don't sample fast enough, you lose a lot of this detail. So you lose these spikes. Even at 10 hertz, you're losing a lot of detail here. And that can lead to erroneous assumptions about the way the behavior is going to occur. So they also were collecting data from real machine tools. So at the same time they were sort of setting up this rig, they were collecting data and running these processes on machine tools, and then looking at recurring machining cycles. So this is a single set of operations, spin up, spin down. So we look at the way we look at sort of in a broken down form. This is your machine startup time right here, and then you spin everything up, and then you're ready for operation. This is when you start your spindle, that time right there, and then your acceleration, your main accel, and then this is motion to get to that point, and then this is when you actually start removing material, back down, and this is your power down, your spin down, and so forth, and machine off. So these were the fixed power. This is the operational power, meaning this is the amount of energy it takes to be able to spin the spindle, and this is the amount of tooltip power. They said this is, I guess, based on simulation and theory, how much power it actually takes, and I guess the unproductive power is the delta between those two. And then they looked at a real machine tool and said, hey, let's try to find features. And let's be able to identify features by just looking at the power data coming off the machine. And that's where these things were. So they found these different patterns to be able to find the feature sets within the data. And they could see the motor start, the load levels as the cutting depth increased. Rapids exhibited this type of pattern where you had these nice little spiky bits coming out. So, low level operational power, but spikes. And these are your cutting powers. Fun part was when they actually started comparing it. This is their simulated on their simulator after they were able to collect all this information. And the actual, they were actually able to get within very, very close to the actual. So here's their actual simulated. This is what they did off of their rig by basically reverse engineering the machine and building a model for those different power levels. and then putting it back into the feature sets and understanding how those features exhibited various different loads and speed changes. And basically, these were the two fits, and they got pretty damn close. So again, that was taking data coming off a machine and understanding what it was doing, and then looking at just power data coming off of it, being able to fit it, and then reversing it out and simulate it. The next step of this is basically, now I don't know what the process is. Can I come up with just a simulation of any machine tool out there? So I can create basically, you know, an n-axis machine with various levels of complexity, but I know the basic behavior of that machine. Can I simulate that from base principles? And that's where they're going. And so, I mean, that's the basic idea behind this. So you can do that once you understand the data and you understand processes and understand what's happening. The other one that was interesting, we did a 3D printing project out there where they were trying to find out, this is just a simple little, you know, cheap 3D printer, plastic printer. And the idea was, what is most highly correlated to quality and strength? So you think about it in 3D printing. Now, this is used MTConnect as well. We don't directly support 3D printers today, but MTConnect is extensible, meaning that you can add additional data items to it if they don't already exist, and that's what they did. So they need to add a couple for 3D printers. But the idea, again, was sensor fusion, taking data from the sensors and motion and so forth, which is actually very similar to machine tools, and being able to apply it. So they did a series of experiments, and they used off-the-shelf software, open source slicer software, and reviewed literature and so forth, and then took a look at a number of different parameters for dimensional accuracy: temperature, PID values, slicing, well, various different things. I'll go through them right now. And they worked on, there were 7 variables associated that they looked at. And they built this little cube here to do the testing. And they used just a simple vernier caliper to do the testing with 10 micron accuracy. And they also used a tensile strength tester to be able to make sure that to test the strength of the part. And what they were looking for was, from things like, you know, extruder temperature, infill patterns, and various other things like slice height and density, what was most highly correlated with the strength and quality of this part? And again, I could put you in touch with these people. They found that there were some variables that had very high significance. So for accuracy, this is the accuracy analysis. Let's see, I'm just going over this, sorry. The X and Y axes had opposing importance, and I'm not quite sure. They say the intercept had high significance. So basically they found that certain things were highly correlated to the accuracy. And I think temperature was also, so slice height was a strong predictor of the tensile strength, but had little significance for modulus, and infill density had, was a predictor of modulus, but not too much of tensile strength. So there were some things here that were kind of expected and some things that were unexpected, as well as temperature was modulus, but didn't really seem to have a big predictor for tensile strength. So there's more information on that out there. Anyway, I can point you at it if you're interested in that project. But anyway, it can be used for interesting 3D printing projects as well. There's some other work going on in that space as well. So that's most of it for the first part of this thing. You can go into the standard itself if you're interested. You want me to go dig deeper? Basically, from the standard itself, we have 4 information models. We have what we call devices, which is a model.
Okay, so Will has asked me to pause here, and I think he either has something to say or you want to just give a chance for people to ask questions at this time. Will, are you back?
Yep.
Are you back on? There we go.
Should be. Yep. Just want to see if anybody has any questions about the, one second, the research or anything else that we just covered. We're out there.
Okay. Nope. No questions.
Nothing yet. Okay,
right.
so let's keep rolling.
We'll keep rolling then.
Of the manufacturing equipment itself. It's what's called a logical model. And streaming data that comes out, this is time series values time-stamped, which describe each one of the data items you can get from each one of the components and the data about it. We have assets, which provide a key value pair of data. That's for things like tooling data and for processes, and then just some protocol errors. So does everybody know a little bit about XML? A little bit? Okay, so the reason we chose XML at the time, it was first off the prevalent standard for standards. And it's very easily extensible. It also has verification built into it. So you have standards like schema, which allow you to be able to validate that it's correct. And it's fairly human readable. We've actually made MTConnect as readable as possible by sticking to some basic principles for naming of elements and attributes where they have to actually have spelled out words. We only have a couple of abbreviations for them. And we do use schema so you can do full validation, and we also use Xpath to be able to express the, to be able to focus on certain aspects of it. So I'm going to go quickly through this. Basically, you have elements and attributes. Elements can have sub-elements, and they can be nested. An attribute is basically a key value pair within an element. So it allows for an association. It's basically some additional information around the element. And then there's data within the elements, like C data. If you look at HTML web pages, it's actually an XML document. Or you could have more nested elements, or you can even have mixed content. Like in HTML, you have C data, text, and then elements, and then more text. And each element needs to be closed with a closed element. So if you notice, there's an open, and then there's a closed. There are some shorthand versions of that where you just have, like, this is a simple element with just a slash at the end. It just stops you from having to put a closed element when there's nothing inside. All of our elements are in camel case, meaning the first letter of each word is capitalized and they're put together. Attributes are called snake case, where the first letter is lowercase and each of the words are capitalized and they're glued together. And the values are all uppercase with underscores in between. Just makes it consistent, and whenever you look at it, you know what you're looking at, and you know what the patterns are. We also have this idea of grouping, like in devices, components, data items, etc. Pluralized words are usually used as grouping elements. So just some basic rules. When you look at the standard, it gives you sort of a high-level idea of what's going on. And with Xpath, we can then select various different pieces of the document. This allows us to focus on, let's say, one component. I can say, give me all the data just for the controller, or give me all the data just for the axes. And by wildcarding it, and these are based on attributes, so, you know, whatever at living based on this guy right there. So devices. This is called a probe request. And devices provide the logical structure. So it's each one of the components in a hierarchy. And the component's names, the element name describes a component, like axes or linear, rotary, controller, path, etc. And we provide the data items that go into that. So each of the data items has a certain syntax, a certain set of units, and that the units are always the same. So we've normalized all the units. And you can nest the components to be able to give additional structure to your device. And this model, what we call devices model, is MTConnect devices as a root element, only has this meta information. It doesn't contain any data, just information about what the data is. So if you look at a device, it's basically broken down this way. You have a device has availability and emergency stopper usually at the top level. Then you have a set of axes, and then you have controller, and the controller has a path, and the path allows things like program execution, controller modes, blocks, and path position with free space position. Yeah?
Does it only support 4 axes?
No, it supports N. You can have any number or combination of these. So you can have linear and rotaries, and you could do a robot with, a series of rotary axes joints. We don't support a full kinematic model. We're waiting for another standard to actually give us a kinematic model. We also support things like systems, so electrical, hydraulic, pneumatic systems, and we're getting into things even like accessories, robot loaders, like small loaders or built-in components.
Do you
Yeah.
support anything within values usage data, like point clouds and things like that?
Well, point cloud is made up of a series of time series points, effectively, right? So let's say you were trying to collect the path position and use that as a 3-space position as a tool, as the spindle or the tool traverse the part. You could use that tool to position to be able to construct a point cloud, and we've actually done this to understand every single point that tool traversed and reconstruct the shape of the part.
Well, I'm talking about depth camera data.
We don't have camera data yet.
Okay.
It's something you could actually extend out to if you wanted to.
Okay.
No, we haven't gone into imaging or anything like that. This is what it actually looks like. So you have your devices, there's a protocol header, and your data items, and your axes, and so forth. One point on that. So the idea here was mainly streaming data. So point cloud data, files, and other types of information models, we're looking at more sort of in the asset space than in this space. So this space is primarily, this is data that's going to be streamed out real time from their processes. So each one of these data items will be given as it changes. So we do what's called delta compression. We'll talk about that in a second with some of the streams information. But if the data doesn't change, we don't write it out. So every 100 milliseconds, we don't push out the same data each time. If the value hasn't changed, we don't communicate. Every document has to have a top-level element. So in this case, we have a streams element. And if you look at the document, basically,
I'm going to pause it right here because, Will, we have a question that I want to make sure we get before we get too much past here. So if you could come back on and let's see. The question is, do you have an example or link to this point, cloud/time series application? I hope I'm asking that question right.
Point cloud. We don't have something like that. We have some analytical tools that we could share from some work that we did with VRTK, which allows you to analyze large amounts of MTConnect data up on Amazon. And we're going to be posting, actually, as one of the follow-up webinars, some links to some of these tools of how to use the AWS IoT tool sets to be able to do this type of analysis. So I'm not sure if that answered the question.
Okay. So I'm not seeing a response yet, or another question.
Okay.
But I'll go ahead. So actually, I think, is this a natural stopping point? Because I don't, we still have quite a bit of time left. We still have a half an hour left of, of at least getting into other things. And you know, we like to try to keep these under an hour, and we do have some other some questions and finishing up that we want to do. So, so if it's okay with you, Will and Tim and Helena, if you want to come back on, I'm going to put my video back on. Guess I can take my glasses off here, and we can stop right here for today, and then schedule another time to come up and you know, a third webinar to come up and finish everything up. Like I said, we're of course recording everything, so we hope you can come back. We don't have a date set up exactly just yet, but we will try to set it up for next week if possible. So what I want to do though is we have received some questions from some of the people, you know, over both your time when you were doing these presentations cross country, but as well as on the webinars. And so I'd like to ask a couple of these questions and see what we can see about getting the answers. And then those of you that are also online right now, feel free to stick some more questions in here too. So to Will, one of the questions I have is, do you need to participate in phase 1 ideation in order to participate in phase 2 application? Do you have to do that?
No, actually you can pick and choose. You can either do ideation, application, or you can do both. The other thing you can do is if you have a really good idea, you can use it for both your ideation as well as your application project. So let's say you're working on your master's thesis or your PhD thesis, and you want to use it as part of this challenge. That's fine. And first, just write up a 5-page summary or a 5-page overview of your project, and then submit that for the ideation in a couple of weeks, and then develop a application example, just sort of alpha level, of your project as well, and then submit that as the application. So it's pretty easy to get started with this thing.
Okay, and we did have a follow-up here on that question. You know, so we could use this to analyze point cloud data. That refers back to the question you were answering. The answer is yes?
Yeah.
Yeah.
Yes, the answer is yes. We did a project. This is another research project that was done over at another IIT Madras project, where they were able to pretty much reverse engineer the part by analyzing point clouds. So in MTConnect, I'll just give a little bit of, we haven't gone this far in the information model, but there's something called the path position, which is the control point of the machine tool. So basically the point at which the tool is cutting metal. And that gives you an instantaneous position of where the machine tool is relative to the material or in space. And when you take all those 3D space points, which you can get from most machines, you can actually reconstruct that point cloud. So there's some tricks and techniques around that, but yes, you can use MTConnect to be able to actually give yourself a point cloud of everything the machine is doing. And at each point as well, you can do things like analyze feed speeds. If you have sensor fusion, you can analyze energy, vibration, acoustics, anything else, any other data that you want to have associated with that control point.
Okay. And I'm going to bring in the slides that have the follow-up information of where they can get some more stuff. But Helena, I also have a question for you, and that is, you know, do you have to be a U.S. citizen to participate in this? Oh, you need to unmute yourself.
Okay.
There we go.
Anyone who, excuse me, anyone who is any student at a U.S. community college or university who is lawfully admitted into the United States is eligible. So this includes international students, U.S. green card holders, as well as citizens. So citizenship is absolutely not a requirement.
Okay. All right. And I think Tim's, I don't know if you're online, Tim. I just want to double check. I think Tim's camera is kind of giving him some funky deals here today.
Yeah, I'm still here, buddy.
Oh, he's here. Good. You know, I guess I have a question for you, Tim. If I'm going for my GED, can I use this for? Never mind. Anyway, and Helena, another one. Who funded this challenge? Where did the money come from?
The funding source, the sponsors of this challenge happen to be the Office of Secretary of Defense, Defense-Wide Manufacturing Science and Technology program. This is actually the second MTConnect related student challenge, MTConnect related challenge that this program has funded. And
Yeah,
we're
that's
very
right.
excited and grateful for that.
Yeah, of course. That's very cool. That's very cool. And let's see, can submissions, I don't know if you answered this question already, Will, but because I know you said that somebody, they can do one, they can do the ideation, they can do application, those could be separate, or they can be the same. But I guess I might have missed, can they use a current project they're working on to do this?
Definitely. Definitely, yes.
Okay.
You can use existing material, past material. You can use, anything that you've been working on to support this project. Not commercial, of course, but any project that you've been working on.
Okay. Okay. I don't have any other questions. Elena, go ahead.
I would like to add one thing here, Steve. Students can enter the competition any number of times. There's no limit as to how many submissions they could have, both for ideation and application. And we encourage teaming within the university or within the same school as well as across schools.
Oh yeah, and that's important stuff. I'm glad you brought that up. They can do it with teams, and they can also submit multiple applications. So good for them. So notice that I had the slide up here of the links to the web pages for the for the student challenge, and then also here where I have Elena's contact information. There's also a Facebook page that you can go to that is about the student challenge, or is it about MTConnect or something like that? But anyway, it's where you can also submit some questions in there. Let's see, and I'm getting a message that there's some links at the end of the presentation. Let me see which are you talking about the presentation you were going to give, Will? Because I'll find that.
At the very end. Yeah,
the very
end of the presentation.
Okay, let me.
There are a couple of resources that we can also give people. Let
me pull that up, and I'll get us down
to
the end of the presentation. Let's see, because we'll be going through this again next. We'll be going through this next time.
Mm-hmm.
So okay, so here's the resource page I think you're referring to, correct?
Yeah. So for some of the research, there's also things like our studio, which we use, and those are links to things like if you're doing machine learning or in kind of data analytics. There's Microsoft has a really nice platform on Azure, as well as Amazon has some really great tools. And we've developed, as I was mentioning, some scripts for R, which we put out a paper on, and it's in our blog from what we call the VRTK, which is how to use MTConnect data with R. And if you go to the next slide also, there are some, let's see, actually the previous slide to that.
All right, the one before that?
Yeah. So MTConnect also provides a number of free and open source projects that are available from GitHub. So you go to github.com/MTConnect. You can start looking at some of these. The agent itself is open source and available for free download with builds already available for Microsoft Windows, and it also builds on Linux, and there's some links to how to do that. As well, there's various different technologies for working with MTConnect, and if you look at, there's an adapter and an application lab from MC2 with videos on how to set those up and how to create your own MTConnect technologies. Joel Neidig has donated an example for how to use Google Glass, which was pretty cool. Wow. And if you want to play around with that, as well as a Unity 3D demo for Microsoft Xbox. So lots of tech up there, which tells you how to use MTConnect, which can show you quick and dirty ways of using MTConnect, and it's all free, open, use it. Licensing is very liberal, so feel free to incorporate it into any of your projects.
Okay, great. And I know there's something here about getting started.
Mm-hmm.
You want to comment on that?
Yeah, sure. So, yeah, the easiest way to get started with MTConnect, there's some open, resources, agent.mtconnect.com, which is always streaming data from MTConnect, and you can just pull that data in. And the easiest way to look at it is just to get some of the XML directly from the agent and start playing around with it, and then convert it into like a CSV file, and then start using things like R or other analytical tools to start playing around with the data. That'll give you a good idea of the shape and the feel of the data, and then think about what you want to do. I mean, again, the first webinar went into some of the drivers from the industry, so think about, how you could use this data to help an SME become more efficient or solve some manufacturing problem using data, sensors, and other technologies that are now available. And
Okay,
as we said, we're going to be doing more videos on this stuff. Yeah.
Yeah. So we'll be doing, the final webinar probably within a week, and get the rest of the information out to you there. We will also be sending out emails to everybody that's been registered, and as well as, I guess, we'll be sending them out to everybody about where they can watch the archives of the first webinar as well as the archive of today. And I am going to guess that we're also going to be providing them with the visuals. Is that correct? Or is that not correct? Yeah, I see somebody nodding.
That is correct.
Okay, good, great. So, we've reached the end of our time for today. We've gone a few minutes over, but thank you everybody for joining us. Thank you, Helena and Tim, Frozen Tim, and Will, of course, Godfather, for joining us today. And we look forward to seeing you guys again next week in the final webinar of the series. And of course, we'll be putting all the information online for all of you and getting that out to you as well. Thank you so much, you guys, and we will see you on the internet.
Take care.
Thank you. Thanks for joining us.
Thanks a lot.